For the commercial return, we may invest on the ADC-DSP PAM4 receiver, and we can sell our PAM4 service to all potential customers. However, our architecture or top-level specification is very critical to meet our target. Then, either the design or spec will lead to a slope control CTLE to meet our needs. To meet different channel insertion loss, like 20 dB, 30 dB, up to 40 dB is our goal. Therefore, applying the ADC-DSP based PAM4RX is a must. But we need to design the ADC resolution requirements for the target insertion loss, since we are also working on the highest data rate up to 224 gigabit per second. The ADC could be power hungry if we also design on a high resolution ADC. How do we consider it? Correct. Signal to noise ratio, SNR. We could model the SNR in different ADC resolution, along with the channel loss, TX and RX front-end equalization, and the required bit area target. Intuitively, if both TX and RX front-end provides a higher equalization boost, then the residual RSI would have a less signal dynamic range, which may not need a high-resolution ADC under the target bit array. For a TX, there's not much we could do if that's a link partner, but we could try to improve our front-end equalization, which is the CTLE. What's a reasonable boost target of CTLE for the 40 dB channel loss? Yeah, perhaps 20 dB, which is half of the total loss. Then a 6 bits or less resolution ADC may be doable. Unfortunately, a 20 dB peaking gain or boost the CTLE could be challenging in a low supply voltage 5 nanometer process. What can we do? Bingo, just make 2 stages of CTLEs, which should be easy. Are you sure for 224 gigabit per second with more than 56 GHz required peaking bandwidth? Of course not. 6 more stages will shrink the bandwidth, even just 1 stage more. Alright, what's more? Yes, you must apply the inductive peaking besides the source degeneration inside the CTLE, and then enhance the boost up to 20 dB. Interestingly, this Intel paper used a complementary structure to maximize the transconductance for given biasing current. Of course, the 4-stack device may have the Henry issue, and we may need to raise the supply voltage high enough, which is roughly 0.9 volt in the reference. In addition, the degeneration capacitance can control the mid-frequency slope of the transfer function, which the shunt inductor determines the frequency gain at peaking frequency, roughly or greater than 56 GHz. As you can see, varying the CD controls the CTLE slope response, which could better match any channel slope without over-equalization or under-equalization with just 1 stage. Amazing? Right. The reference also demonstrates the slope control of the CTLE in silicon to match the channel behavior to minimize the residual RSI in the ADC input. This less residual RSI then helps reduce the dynamic range requirement from the ADC and relax the required ADC resolution to just 6 bits. In addition, there are 2 stages wideband VGA after the 1 stage CTLE that can support a raw DC gain to better linearity requirements at the ADC input. Then the peaking gain between the 56 GHz and DC could be further increased and equivalently reduce the ADC input dynamic range. Let's look at more measurement data from their result. The RX was tested with the input data of 224 gigabit per second PAM4 PRBS31 pattern using a TX to RX external loopback. The transmitter has 1 volt swing and is equipped with 4-tap pre-FFE equalizer. The RX FFE was enabled, but the RX DFE was not used in this measurement. The bit array measurement was repeated across 4 external loopbacks in 20 dB, 27 dB, 31 dB, and 38 dB. With the measured bound-to-bound insertion loss, this loopback setup achieves bit array with 1E-11, 5E-10, and 6E-7 respectively. Unfortunately, the JTAL was measured at a 224 gigabit per second rate with only 32 dB loss. As you can see, the JTAL has a jitter peaking because of the long RX digital FFE latency. In addition, this peaking causes the JTAL may not have a slightly good margin on the JTAL mask. Here are the summarized images showing why we need the slope control CTLE in ADC-DSP PAM4 RX. To meet different channel insertion loss, we may need higher ADC resolution, but the power could be very high at the ADC for 224 gigabit per second PAM4. To reduce the ADC resolution, we can improve the analog front-end CTLE and reduce the residual RSI such that it helps reduce the dynamic range requirement from the ADC and reduce the required ADC resolution to just 6 bits. The most effective way is to apply the inductive peaking in addition to the source degeneration inside the CTLE and then enhance the boost up to 20 dB or higher at peaking frequency, roughly or greater than 56 GHz by shunt inductor in just a single stage. Therefore, varying the CD controller CTLE slope response to match any channel slope without over-equalizing or under-equalization at the ADC input, which has a minimal residual RSI. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.